It's a pleasure to welcome Professor Katherine Blundell to speak to us this evening. She's a professor of astrophysics at Oxford University and a research fellow at St. John's College. And her research interests really span a very wide range, and she has done extensive work and published extensively on evolution of active galaxies, radio galaxies, quasars, which she's going to speak to us about this evening, their life cycles, accretion of material near black holes, astrophysical plasmas, launch and propagation of relativistic jets. She has worked extensively on this very enigmatic object, SS433, and she uses data across the electromagnetic spectrum, both imaging and spectroscopy, as well as computational techniques, plus theoretical interpretations of the exciting things which she observes. She's also been very active in popularizing the field, and she has this program which sets up optical telescopes to observe jets, and several of them are there across the world. She has received recognition for the wonderful work she has been doing. Her awards include the Philip Leverhulme Prize in Astrophysics, the Royal Society's Rosalind Franklin Medal in 2010, the Institute of Physics Bragg Medal in 2012, and the Royal Astronomical Society's Darwin Lectureship in 2015. In 2017, she was the Queen's Birthday Honors. She was appointed OBE for her services to astronomy and the education of young people. And that is something which I've seen over the years, that it's something which she's extremely passionate about. In 2019, she was appointed Gresham Professor of Astronomy. And it's a real pleasure to have you with us this evening and speak to us about radio galaxies and quasars. Thank you very much, Katherine, for making the time just before Christmas to actually just speak to us. Thanks a lot, Katherine.
My great pleasure. Thanks, Sykes, so very much for your kind introduction and for the invitation to connect to the radio community across India and beyond this evening. Well, good evening, everybody. And I'm sorry we're not able to be together in person, but how super that we can connect thanks to the wonders of the internet. So Sykes asked me to speak to you this evening about radio galaxies and quasars. And I thought I'd begin with this image of a cloud structure above the GMRT during my last visit there, which reminded me so much of a radio galaxy. I thought I couldn't walk past without photographing it. So I hope this brings for you happy memories of visits to the GMRT for you as well. So radio galaxies and quasars, what do we see and what's out there? Well, I'm sure I don't really need to remind this audience of the fact that there is so much more in outer space than what we can see with our eyes. And you're focusing particularly this week and next week on the radio waveband, which is such an interesting and such a rich energy band to study. But in today's talk, I'm also going to be connecting up with X-rays because sometimes that can inform us a bit more about radio plasma. So I'll bring that in later on in my talk. The only difference, of course, between these different wavebands is just the wavelength of the photons that our telescopes and our receivers are actually detecting. Nonetheless, these different photons from these different wavebands really does inform us about different physical mechanisms that are taking place in the different objects. And I want you to keep in mind that to get a full picture of the activity of what radio galaxies and quasars are doing, we need to keep in mind the whole spectrum of radiation, not just exclusively radio, but also optical, infrared, and indeed X-rays as well. And I'm going to illustrate this point by showing you 3 images at different wavebands of the same bit of the sky. Look at the central panel first, and I wonder if you can see the Orion constellation in the middle of that image. The moon is up there in the top of the middle panel, which distracts us a bit. But I want to begin by reminding you that when we see optical emission, that's telling us about the locations of fusion in the universe. Stars, of course, are undergoing fusion as we speak. But in the radio panel on the left of the exact same region of sky on the exact same angular scale, that's telling us about the distribution of magnetic fields in the universe, because a lot of the radiation that's associated with radio galaxies and quasars arises because of very energetic electrons moving in the presence of magnetic fields. And as they try and move through those magnetic fields, they undergo forces which cause them to undergo helical paths and release synchrotron photons, which we receive as radio emission. So radio tells us about the presence of magnetic fields of magnetized plasma in the universe. In contrast, X-rays on the right tell us about the distribution of hot thermal plasma and where gravity is at play. And so I really want to emphasize that to get a full picture of what's going on, we need to keep all of these different wavebands in mind. So now let me start with the optical view of the most famous radio galaxy, Cygnus A. This is an optical view of a region of sky that I'll show you the radio counterpart of in just a moment. And almost all objects that we're seeing in this image here are stars, except one, this central one that when I zoom in, we can see that it's not a point source, but it's an extended fuzzy blob. It is itself a galaxy of hundreds of thousands of millions of stars. But at the very center of this galaxy is a great big black hole. And if we look at this exact region of sky on the exact same angular scale, but now at radio wavelengths, this is what we see. That central black nucleus region is absolutely coincident with the center of that fuzzy galaxy that I showed you in my previous slide. And what you'll see, of course, is that either side of this central nucleus are two great big balloons of radio emitting plasma. There's a lot that we can say about this, and there's a lot we can say about radio galaxies and quasars in general. First of all, I want you to appreciate the size scales that we're talking about with these objects. The length scale is something like 100,000 light years. So the time scale to grow this big is something like 1,000,000 years, depending on exactly what you think the expansion speed is. And at the heart of everything, responsible for the collimated jets that inflate those balloons, is a supermassive black hole, a black hole whose mass, we think, is almost 1 billion solar masses. This is a very iconic object, Cygnus A, but there are so many other beautiful examples. This is 3C353, and in each case, these objects are characterized not just by their extreme size, but the fact there are two oppositely directed jets squirting away from the black hole. This is NGC 6251, imaged by Robert Lang, who's part of the Square Kilometre Array Observatory. And you can see these exquisitely detailed images of these jets. The sky is absolutely full of them. Here are a number that I've imaged myself. And what you see is that they're invariably characterized by oppositely directed jets. Sometimes these jets are very knotty, as in the current example, and sometimes these jets are much, much smoother. Now, before I go ahead and start explaining how some of these things work and what their characteristics are, I just want to be clear about the nomenclature that we use for radio galaxies. So the compact region in the middle is sometimes referred to as the nucleus, but sometimes referred to as the core. It's the center of everything, the location of the black hole that's responsible for squirting out the oppositely directed jets. These big extended bubbles of radio emitting plasma, they are called lobes. And the brightest bits on the outermost edges are called hotspots. That's where these jets shock on the intergalactic medium, causing particle acceleration and then flowing backwards towards the core, inflating these lobes as they do so. I want to be very clear what the spectral shape of these different regions is for each case. So I'm plotting on the panel above the image, flux on the vertical axis, and then frequency along the horizontal axis. Now, for the lobe itself, which is, even on spatial scales, very, very dominant energetically and in terms of luminosity at frequencies below, say, a gigahertz, certainly by 100 megahertz, the lobes are what are energetically dominant. You see a very, very smooth spectrum, which often is quite curved and gets steeper and steeper. In contrast, the compact core often has a very turned over spectrum, or sometimes it's really quite flat, but it's usually not steep in the way that the lobe is. And so the lobe spectral shape will vary according to the redshift that one of these radio galaxies is located at, in the sense that the higher the redshift, the further the radio galaxy is away from us, the more dense the cosmic microwave background radiation field, and so the greater the inverse Compton losses and the steeper the lobe spectrum will be. In fact, there's also a dependence on the luminosity, the intrinsic jet power of each radio galaxy, in the sense that the more luminous, the more powerful a radio galaxy is, the stronger the magnetic fields will be in the hotspots and the steeper the lobes will be. That's a fascinating area of study, which I've enjoyed researching quite a lot. There's a big paper that I wrote with Steve Rawlings and Chris Willott in 1999 about that. But I want you to appreciate that if you make an observation with the GMRT or with the VLA or any other radio telescope, if you make a survey at 100 megahertz, you will have a survey of very different objects compared with if you do a survey at 10 gigahertz. At 10 gigahertz, you'll pick out lots of compact objects, lots of objects with a turned over spectrum. If you make a survey at 100 megahertz, you will see lots of these extended radio galaxies and quasars, because it depends on in whichever frequency band, which actual component of these objects is dominant. So it's really important to keep this in mind. But I now want to turn to the fact that there are different structures of radio galaxies and radio quasars that are out there, which have a very strong dependence on radioluminosity. So I'm plotting here on the vertical axis luminosity at a frequency of 178 megahertz. The most luminous radio galaxies at this frequency have a structure that we call an Fr2 structure. Sorry, I went backwards. Have a structure that we call an Fr2 structure. Whereas below this luminosity, the structure is what we call an Fr1 structure. The key difference is that the Fr2 has these very bright, compact hotspots. It has two of them at the outermost edges of the radio structure, whereas for an Fr1, the luminosity declines as you go away from the core, and there's no compact, bright hotspot at the outermost edges. Now, this dependence on radioluminosity of structure, do you have hotspots or don't you, is one of the most robust dependencies in all of astronomy, not just radio astronomy. It's incredibly important to keep this in mind. Steve Rawlings and I explored this some years ago, and we looked at the dependence of gigahertz radioluminosity. I'm plotting 5 gigahertz radioluminosity on the bottom axis and 151 megahertz on the vertical axis. And for the typical spectral indices, the typical spectral shapes that we get for lobes in radio galaxies, I've plotted those as diagonal lines. The three lines together pretty much span the space for most radio galaxies that you're likely to be able to find. So if I plot on that axis for the high radioluminosity Fr2s and the low luminosity Fr1s, you get a sense of how that fits in with the sort of spectral indices that we're thinking about. But it's important to appreciate, particularly when we're talking about quasars, which are optically much brighter than radio galaxies, these are often observed and found more easily at gigahertz frequencies. And again, the more luminous ones being radio loud and the less radioluminous ones being known as radio quiet. If we put the two together, we get a sense of how Fr1s, which are objects that are really characterized by their low frequency structural shape, as compared with Fr1s, and how radio quiet quasars and radio loud quasars are really clearly seen at gigahertz radioluminosities. And that big green star there is the location on this plot of gigahertz radioluminosity against hundreds of megahertz radioluminosity of a radio quiet quasar studied with Tony Beasley and Jeff Bicknell. This particular radio quiet quasar was quite exciting because we were able to demonstrate it has a jet in it that is relativistic, just like the jets in radio loud quasars. So it's very helpful to keep this sort of plot in mind. But back to the FR division, the Fanaroff-Riley division that I spoke about. Sometimes it's easier to simplify things with a cartoon. So I'm showing you on the left 2 examples of Fr1 radio galaxies, and on the right, the Fr2 radio galaxies. You can see the 2 brighter outer hotspots here. And again, the Fr1s are seen at low radioluminosities at frequencies of 100 megahertz, and the Fr2s are seen at high radioluminosities at frequencies of a few hundred megahertz. The leftmost structure is known as a twin jet type of Fr1. Then we have a fat double, sort of a bit more balloon-like Fr1. But on the right, the Fr2 that we see is known as the classical double, the Cygnus A type of classical double Fr2 radio galaxy. Now, what are some of the other differences between Fr1s and Fr2s? Well, the jets are really quite different. In Fr1s, which are the twin jets which fade away from the nucleus, the jets are very lossy and very dissipative. So we see them quite clearly close into the center, and then because they're so lossy and dissipative, they fade as you go away from that central point. In contrast, the jets in Fr2s are not lossy. In fact, a key observation is that the jets in Fr2 radio galaxies are very faint indeed. If you remember back to that image of Cygnus A, the jets are really faint, but the lobes are very dominant. There are differences in the host galaxies, the environments in which these radio galaxies both grow. And we think that that's a lot to do with the amount of gas that's around to fuel the black hole that is at the center of both Fr1s and Fr2s. But it's important to note the similarities between Fr1 and Fr2 radio galaxies and quasars. The first similarity is that of size. There are examples of both Fr1s and Fr2s that are megaparsecs in extent. So let's look at an Fr2 quasar. This is the first quasar I ever published a paper on. My first ever paper was on this quasar, 4C 74.26. It's over a megaparsec in extent. Now let me show you a snapshot from the NVSS survey made at the VLA some years ago. This is what so a snapshot with the NVSS had an on-source integration time of, I think it was about 23 seconds. Now, it's true for any radio telescope. If you don't take a long enough exposure, a long enough integration, you're going to miss out on the complete picture. So let me now show you this same Fr1 radio galaxy with a 2-hour observation on the exact same Fr1 jet. This deeper integration reveals a jet that's over a megaparsec in extent. This was work by Fraser, Owen and co. And you can see the jet even processes round. It's beautiful. You can just about see it in hindsight in the snapshot, but you wouldn't really believe it unless you'd taken an image that was deep enough and high enough quality. Let me show you now an image from the Meerkat in South Africa. This was opened about 3.5 years ago, and it's taken some wonderful images. I want to show you this particular Fr1 radio galaxy. You can see it's bright in the middle, there's some knots, and then it fades as you get further away. But this image by Mpati Ramatsoku shows clearly that there's so much electrical activity with all these spurs of plasma linking across the two different lobes that just invites us to investigate how radio galaxies and quasars are working and how they are evolving. It's really important, this business of, are we making a faithful, a high fidelity image of the structure that is there? And I'm sure during the course of this week and next week, during your winter school, you will be studying the benefits, the merits of using an interferometer and potential pitfalls as well. So here is one I want to show you. This is a particular region of sky, again, from a 200-second observation with the VLA in its so-called B configuration. So this is quite an extended configuration. It's got lots of long baselines that give you high resolution. And now I'm going to show you on the right-hand side the exact same region of sky, but with shorter baselines. This is honestly the same region of sky. You can see that point there, that point there, that point there, and that point there, mapped to 1, 2, 3, 4 here. But this bit is completely absent from over here. What's the difference? Well, the one on the left lacks short baselines. The one on the right has short baselines. It's taken in the D configuration of the VLA. And it's important to remember that an interferometer is blind to structures on size scales that are not sampled by short enough baselines. I'm sure you'll be hearing a lot about this in different contexts this week and next. But back to the jets in radio galaxies and quasars. Why are these jets important? Well, they tell us about the extraction of energy from a massive black hole and from the accretion disk surrounding that black hole. At the outermost edges of the jets, we see acceleration, particle acceleration, to some of the highest energies of any particles in the universe. My colleague Tony Burl and I believe that these objects are responsible for some of the ultra high energy cosmic rays that eventually make their way to Earth. They certainly tell us, jets certainly tell us about the transport of energy to megaparsec scale distances from the central black hole. And this is all something that's known as radio mode feedback, to re-energize the intergalactic and intra-cluster environments. It's critically important, if you want to understand the formation of structure in the universe, that you pay close attention to the life cycles and the evolution of radio galaxies. They redistribute energy and heat. They ionize hydrogen. And if you have ionized hydrogen, that hinders the formation of stars. So radio galaxies matter for whatever field of astrophysics you're interested in. Jet physics is of amazing astrophysical interest in its own right. And Robert Lang, whom I mentioned earlier, has developed really important techniques which make use of the fact that one jet is coming towards Earth and the other jet is going away from Earth. And in both total intensity images and polarized intensity images, the fact that you've got oppositely directed jets whose axis is 180 degrees different from one another compared with your line of sight to Earth, give you powerful constraints on the underlying jet physics. He has modeled these in beautiful detail, and we've really learned so much about jets from all of his work. I'm rushing through this now, but a summary of what we know about Fr1 jet properties now is that the flow speeds in all the different jets are very different in different sources. Sometimes they're only 10% of the speed of light. Sometimes they're much, much faster and a whole lot closer to the speed of light itself. In Fr1 jets, the radio synchrotron seems to extend all the way to X-ray synchrotron. There is ongoing particle acceleration along the jets in Fr1 radio galaxies. The jets are very light. We think they are electron-positron as opposed to electron-proton. The B field is both longitudinal along the jet and toroidal around the jet. And if you want to get started in some of this work, the best one to start is Lang and Bridle in 2013. But if you want to learn even more, as I've said, it's important to factor in the X-rays and the radio emission from particular radio galaxies. So let me tell you a little bit about the X-ray properties of radio galaxies. There are two types of X-ray phenomena that are associated with radio galaxies once you're outside of the nucleus. The nucleus has a whole lot of X-ray emission depending on accretion, but I'm not talking about that today. I'm talking about the jets and beyond. So there are two types of X-ray emission outside that central nucleus region. One is compact, associated with the hotspots and associated with the jets, and the other is very extended and very smooth emission. Compact X-ray emission is associated with shocks where particle acceleration takes place in the hotspots in the jets. The extended emission, spread out emission on the size scales of the lobes, that is relic synchrotron plasma. It is plasma that was previously radio emitting. So back to this big quasar that I talked to you about earlier, 4C74.26. I'm now going to zoom in on the compact hotspot in the bottom of its south lobe. And when I zoom in, I'm going to show you emission from two different wavebands. The red emission here, which you might think of as quite compact. There's a bright compact stripe at the top, and then there's a fainter right stripe at the bottom. That's coincident with these blue contours that are the shape of an eagle or a big flying bird. These blue contours are radio emission from the radio interferometer that we have in the UK, known as Merlin, operated by Jodrell Bank. That's radio emission. The red emission is X-ray emission from the Chandra satellite. So as we zoom in on that compact hotspot, you see this structured X-ray emission, and radio emission is only associated with the southern component of that. Let me remind you that this is a really large megaparsec scale quasar. It's over a megaparsec in extent. And that hotspot in the south, that's over 20 kiloparsecs in extent. And 20 kiloparsecs is pretty big by most other standards. Indeed, we could fit 3 of our Milky Way galaxies inside this hotspot if we stack them in sideways. So the structure of hotspots is very, very interesting in terms of the particle acceleration processes that are taking place. And so what we think is going on here in this giant radio galaxy, which we have a wonderful view into because it's so close to Earth, it's a really low redshift. What we think is going on is described in this paper. First author was Mary Erland, together with some of our other colleagues. What we found was this double shock structure within the hotspot, which was only possible to see because this object was so close to us, as well as being unusually large. So that northern compact X-ray emission is X-ray synchrotron. Fantastically high energy particle acceleration has taken place where the jet first shocked on the intergalactic medium. As plasma flows out of that shock, it fades and expands more, and then it shocks more weakly on the intergalactic medium downstream. But at that point, it gives us radio synchrotron. And associated with that radio synchrotron is inverse Compton upscattered cosmic microwave background photons. The electrons that are responsible for radio synchrotron emission will give energy to the photons that are part of the cosmic microwave background. And that can be a very powerful tool in the toolkit of understanding how radio galaxies work. It's always the case with these objects that any X-ray peaks will be closer to the nucleus than any radio peaks, where we can separate them, where we've got enough resolution to resolve them. But now let me tell you about a different radio galaxy. This one is much higher redshift, 4C 23.56. It's at redshift of 2.5. It's much more powerful. So this one is really much more extreme than the one I showed you. It's still quite giant. It's 0.5 megaparsec in extent. And we published a paper on this some years ago. Here I'm showing you the radio emission as green contours, and the coloured emission is X-ray contours. And you can see again, there are big offsets between the X-ray emission and the radio emission. These offsets are about 35 kiloparsecs. The X-rays are closer to the central engine. The radio hotspots are a bit further downstream by a few tens of kiloparsecs. So what's going on here? Well, we think that the outside of the hotspots, those extended green contours, the extended radio emission, is where you've got freshly accelerated particles in the hotspots that have leaked out into previously energized relic synchrotron plasma. Whereas the X-ray emission tells us about the initial particle acceleration of the jet coming out of the central black hole. But we do also see co-spatial inverse Compton X-ray emission that's co-spatial with radio emission, particularly as you come closer to back towards the nucleus. Let me try and give you a picture that brings all this together. So I'm showing you a plot of the energy spectrum of the synchrotron plasma. What I'm showing on the x-axis is not frequency, but the Lorentz factors of the electrons that give rise to particles of a certain frequency, depending on what the local magnetic field is. And then on the vertical axis, I'm showing the number density of particles with a given Lorentz factor gamma. And so this is the familiar spectral shape. I'm showing it here as a straight line, even though it can be a bit curved, for radio synchrotron emission. These are typical values of Lorentz factors, about 1 million, say, for the typical magnetic field strengths that we think we've got in the lobes of radio galaxies. Now I'm going to show you on this same plot how the inverse Compton scattered X-ray emission appears. This takes place counterintuitively at lower energies. We're now at Lorentz factors of about 1,000, because that corresponds to the electrons whose energy, having gamma of 1,000, will upscatter cosmic microwave background photons at the peak of the CMB radiation into the energy band of the Chandra X-ray satellite. If we consider the two together, then perhaps we can see straight away how the combined study of radio and X-ray means we study the complete spectrum of the synchrotron plasma that gives rise to these lobes. Let me show you another example now, again at quite high redshift, not as powerful as the previous example, but still above that FR2 threshold and almost a megaparsec in extent. This time, the white contours are radio emission and the color scale is X-rays. You can see how you've got the compact radio hotspots at the outermost edges and then showing a little bit of lobe emission. So the radio synchrotron is the outermost bit, and a little bit closer, you've got X-ray synchrotron. But the main part of the lobes in this object is X-ray inverse Compton emission. Inverse Compton upscattered CMB photons by the low energy synchrotron particles having a Lorentz factor of only about 1,000. So not enough energy to give synchrotron radiation that's detectable by the VLA or the GMRT, but enough to upscatter CMB photons, so those photons end up as X-ray photons. So whenever you see inverse Compton X-ray emission, that tells you about relic emission, about previous radio emitting plasma. If we could look at this radio galaxy at earlier times, we'd see it much smaller, the hotspots would be much closer to the nucleus, and we'd see a lot more radio emission filling in the lobes. In fact, there's something very interesting about radio galaxies, which is that their jets can be really quite episodic in nature. And I'm showing you some examples here of a type of radio galaxy that the field terms double doubles, which these images here are by Sykes himself, which show you that sometimes you can see a newly emerging radio galaxy inside of a much older radio galaxy. So if you have a radio synchrotron jet that gives you a wide radio galaxy, then because jet activity can be intermittent, it can be episodic, you can end up seeing these double radio galaxies. And these two are beautiful examples. But how about if we put together the idea of synchrotron plasma that is initially radioactive and then X-ray active, with the idea that you can get episodic bursts of jet activity. I'm showing you now what we call light curves for radio galaxies and quasars in the at radio wavelengths with the dashed line and at X-ray wavelengths in the solid line. Now, unfortunately, because radio galaxies are so long-lived, I said it took over 1 million years for Cygnus A to expand to its current size, but some of the giant radio galaxies and quasars that I talked about earlier, we think they are something like 10 to the 7 or 10 to the 8 or even 10 to the 9 years old. We can't ever measure these light curves, but we can model them. And that's what Philip Mox and Andy Fabian and I did some years ago. And we've applied it to very many radio galaxies and quasars, or we've based our models on very many radio galaxies and quasars, which are in the papers that I've listed on the right. But let's talk about the shapes of these light curves. So the dashed line, as I said, is the radio light curve. A light curve just means the plot of luminosity on the vertical axis and time on the horizontal axis. And if you just look at the dashed line, the radio light curve, it fades and fades and fades, and then when the jets are switched off, it really plummets. Jet luminosity fades with time. In contrast, as you increase the number of electrons that have Lorentz factors of 1,000, you will increase the X-ray emission until such time as you switch the jets off, the jets end their episode of ejection activity, and then that X-ray emission will fade as well. So this is a really important paradigm to keep in mind in our studies of radio galaxies and quasars. The jets are switched on in any given episode for at most 1 billion years. And so this can help us to understand perhaps why some quasars are radio quiet. They seem to lack radio lobes. You still see the optical quasar nucleus, just like you do for radio loud quasars that have the big radio lobes, but maybe it's to do with the episode when we sample the particular quasar in question. If we look at this particular object here, if we sample it early in its life, we will see radio bright lobes. However, if you sample it in this part of its life, there is no radio emission. It's all gone. It's too expanded. The magnetic field strength is so low, there is no possibility of radio synchrotron by any radio telescope. If the magnetic field is gone, you will not see synchrotron radiation. But what you can see is X-rays that are inverse Compton scattered cosmic microwave background photons. And so that's a really important test of this particular hypothesis, that the difference between radio loud quasars, which have the big lobes, and radio quiet quasars, which do not, is that it's episodic. It's to do with the epoch when we here on Earth in the 20th and 21st century can observe those particular quasars. Let me go back to the spectral plot that I showed earlier. So again, we've got gigahertz frequencies on the horizontal axis and 100 megahertz frequencies on the vertical axis, and the typical spectra that apply to these axes shown diagonally. I told you earlier that the most luminous low frequency measured radio galaxies are Fr2 structured, and the less luminous ones are Fr1. The most luminous gigahertz quasars are radio loud, and the less luminous gigahertz selected quasars are radio quiet. Here is that image of a radio quiet, here is the location rather on this plot of the radio quiet quasar that has the relativistic radio jet. It's important to keep in mind that radio jets, even though they're relativistic, can be very low in power. And so we speculate for this particular object in our paper is that it's either just switching on or just declining. And one day we hope to make very deep X-ray observations of this particular quasar to be able to test, is it a quasar where the radio jet is switching off and we'll see bright X-ray lobes, or is it just starting up? And in 1 million years' time, would there be radio lobes and then subsequently X-ray lobes? Well, a prediction of what I've been saying about the episodic nature of jet activity in radio galaxies and in quasars is that you might expect to see radio lobe-less radio galaxies and quasars, radio quiet quasars and radio quiet radio galaxies, if you like. So I'm going to talk now about an object called HDF 130. This is an image at X-ray wavelengths of that object. And in fact, you can see there is a double lobe structure at the center of this active nucleus, which is shown with the green cross there. All these other things are different stars that you can just ignore. So we thought it would be a really good idea to make deep radio observations of this exact field to see if we could see radio lobes associated with these X-ray lobes. So we applied for time on the GMRT and we made a very deep observation. So the center of the previous X-ray image that I'm showing you is at the center of this pink cross here. And what do you see? Nothing. And this is a very high quality GMRT image at 240 megahertz. You can see the high quality by looking at these double radio structures in the far away from the pointing center. There is a complete absence of any radio emission associated with those X-ray bright lobes that I showed on my previous slide. And so we published this some years ago. It confirms the idea that jets will give you enough energy and enough momentum and enough enthalpy that you can have powerful shocks on the intergalactic medium. The backflow from those accelerated particles will fill a huge extended region in space. When the jets switch off, those lobes will continue to expand and expand and expand. So the magnetic field will plummet, no more radio synchrotron, and all you see is X-ray lobes. So in conclusion then, the field of radio galaxies and of quasars is very rich indeed, both in terms of the astrophysics of the individual shock structures, which my colleagues Tony Bell and James Matthews and I think are responsible for the ultra-high energy cosmic rays, both in terms of the jet physics, which Robert Lang and Alan Bridle have studied so much, and crucially, in terms of the energy and the influence that they have on their surroundings. I really hope that you too enjoy studying in the wonderful world of radio galaxies and quasars, and I wish you a very happy and a very fruitful winter school. Thank you very much.
Thanks very much, Katherine, for an absolutely wonderful talk and a wonderful introduction to radio galaxies and quasars. There have been some questions in the chat, so maybe we'll just quickly take them up and then open it up for somebody who wants to raise their hands. There is Sanyukta Agarwal who asked, what would the central region look like in X-rays? This was before you went to X-rays, but maybe you want to briefly say something?
Of course. So the nuclear X-ray emission would be very bright. It would be much brighter in the case of quasars because we think quasar jets are pointing close to our line of sight to Earth. and the accretion disk, which is really what gives rise to quite a bit of that emission, is relatively face onto Earth. We see less of that for radio galaxies which are pointing away from our line of sight. This exact question highlights one of the disadvantages of X-ray astronomy compared with radio astronomy. X-ray astronomy does not bring some of the very fine, high resolution, sub-arc second scale resolution that radio astronomy can bring. So we're a lot more limited in terms of X-ray studies of the nuclear regions of radio galaxies and quasars. But by studying the spectral shape at X-ray wavelengths, and to an extent at X-ray wavelengths, and to an extent at radio wavelengths, then we can start to fit in different pieces of the picture to try and understand what's happening as a whole.
Thanks. Amruta Iyer asks, why are the lobes present only on the two opposite sides of the black hole?
Thank you very much for that. It's all due to the jets. I don't know if I can easily get back to, let me see if I can just get back to one of my earlier images that may help us explain this here. Here we go. So this image here, you can see in, I hope you can see in turquoise here and in turquoise here, the two jets. So our starting situation is jets of highly energetic plasma are being squirted out from the vicinity of the nuclear region surrounding the black hole. Then when the jet impinges on the intergalactic medium, it shocks, forming particle acceleration, and it's that energized plasma that flowing out of the hotspots fills up the balloons, inflates the balloons, which we call lobes rather than balloons.
Is the number of lobes always two, or can it be more? This was asked before you introduced double radio galaxies.
Thank you for that. Well, perhaps I'll comment on that. Let me just go back to your images, Sykes, which we can see here. This one is a GMRT image showing the two inner lobes here, and this one is a VLA image showing inner lobes here, and then an outer pair of lobes here and here and here. So let me take this question further, which is to say we've got some beautiful examples of double radio galaxies here. I always think it would be rather fascinating to make very deep observations, for example, with the GMRT or with another telescope that has got lots of short baselines that won't be blind to the big extended structures, and ask the question, can we see triple doubles? I must admit I'm uncertain at this point whether we should call them triple doubles or double triples, but let me tell you what I mean by that. I mean radio galaxies or quasars where we've seen 3 ejections, 3 episodes of activities. I reckon they might be out there if you were to make very sensitive observations. So the answer to the question is, most of them have 2, a few of them have 4, 2 pairs of 2, maybe some of them out there have a pair of 3. Maybe one of you can research that and let us know in the coming years.
Okay, there's one question on by Gayatri Savarkar on, are these lobes along the plane of the galaxy? Does it have any relationship to the host galaxy?
That's a good question. So one thing I didn't touch on at all is really the shape of the galaxies that give rise to these powerful jets, whether we're talking about Fr1 galaxies or Fr2 galaxies. So let me tell you, predominantly, the kind of galaxy that gives rise to quite strong radio jets is an elliptical galaxy. So elliptical galaxies are triaxial. They're the shape of a rugby ball, or not even the shape of a rugby ball, but they're not spherical, and they're also not planar like a spiral galaxy is. So for most of the galaxies that give rise to most of the jets, there's not such a clear disk. But on the occasions when we do see something of a disk, then typically, but not always, the jets will be perpendicular to that disk. But there are some exceptions.
Okay, so Sanyukta Agarwal asks, how does one determine that a radio jet is relativistic or not? Any particular features one observes in that case? It's a good question.
That is a very good question. So there are a few methods. Let me tell you about two of them. So one method is, it wouldn't work on this particular object, but this will help me explain. So imagine imagine a particular jet like this one, but much smaller than a megaparsec. And you can see they're quite sort of knotty. There are discrete knots within the plasma jet. Or this is perhaps even a better example of knots in a plasma jet. So one way of doing this is to make multi-epoch studies, by which I mean successive observations at different epochs, and then you compare the positions of the jet knots and see if they've moved out. So one thing you know really well is the time stamp for the epoch when you made your different observations. That's about the easiest thing to measure. But then the next thing you measure is the positions of the knots. And if the positions are here at epoch 1 and they're out here at epoch 2, if you know the redshift of the radio galaxy, you can work out the distance that it is from us. You relatively easily measure the angular scale. You convert the angular scale into a physical movement, knowing the distance, the radial distance from Earth to the object. And then you know the physical distance that the plasma has moved over the time interval. Speed equals distance over time, job done. I would mention, by the way, that's been done in the case of, where's it gone, Cygnus A. So Critchbaum and co-workers, using the European VLBI network, so really, really long baselines that can resolve separate jet components in this nuclear region here, they've done proper motion measurements over a timescales of a few years. And in the case of Cygnus A, the most favored jet speed is less than half of c. If I remember correctly, the most favored jet speed is about 0.35 of c. Now, there are some quasars in which this same kind of multi-epoch investigation has been carried out, where you see speeds that are much faster than that. Indeed, so much faster, they're what we call superluminal. They are apparently faster than the speed of light. But actually, that's a relativistic aberration effect, which is pretty interesting. But we don't believe that in reality, any of these jet knots are moving at speeds faster than c. So these kind of multi-epoch studies, which measure what we call, where you can see the motion of particular astronomical features, that's called a proper motion study. That's one method. But the other method is to do the technique that Robert Lang has advanced by comparing side-to-side asymmetries. You'll see, so this, for this model here, the jet coming towards us is much brighter, again because of relativistic aberration, and the jet going away from us is much, much fainter. It turns out that if you model the total intensity and the polarized intensity, that you can make exquisitely detailed observations of the jet speeds and other aspects of the evolving plasma as it moves away from the launch point. This is another way of determining jet speeds. You need very high quality observations. They need to be polarimetric. You've got to be dealing with polarized intensity and total intensity, but that's another way of measuring the intrinsic jet speed going down the middle. So I definitely recommend that if you're interested in this approach to measuring jet speed, this paper is a good starting point, but there's a whole succession of them.
Thanks. Harshini Gadaria asks, a lot of good questions. Any reason for jets being present for at most 10 to the power of 9 years?
That's an interesting question. So I guess what I should say is we don't know of any examples where they have been sustained for longer than 10 to the 9 years. That's not to say they're not out there, merely that it's really quite hard to find them. But that's why the discovery of giant radio galaxies is very interesting. If we could find much, much larger radio galaxies than a megaparsec, maybe we'd have to rethink and start saying, well, actually, they can be sustained for even longer than 10 to the 9 years. So with that caveat that it's possible it could be longer than 10 to the 9 years. And to come back to answering this particular question, I would say that it is probably something to do with either the fuel that's available to feed the black hole and the accretion system, and when that's used up, it's game over. Or maybe there's something about the accretion disk that gets disrupted. If there's, I don't know, a merger with a little dwarf galaxy that just destroys the accretion disk. I'm guessing here, but that tells you we don't really know the answer to what limits the duration of jet speeds, of jet episodes, sorry.
Kaustav Gupta asks that in some of the images, we can see that the lobes change direction, that is, take a turn at a particular distance from the center of the galaxy. What is the reason for that?
Thank you for that. Well, I think the answers are different in different cases. So here's one example here where it's as though the radio jet turned through 30 degrees almost, whereas there's not really evidence of anything other than a fairly linear jet over here. Don't know is the short answer, but just a few guesses here. It's possible that in this sort of region, there's some magnetized plasma from something pre-existing, not necessarily from a jet episode from this particular quasar, but potentially from something completely different that just caused the jet to go off at a different angle. The fact that it's gone off in a different direction only on the north side and not on the south side suggests that it's something local that's responsible. Could either be mass, of course, not just magnetic field, but without sort of focused observations to investigate that exact point, we don't really know. But it's far from uncommon. Let me see if I can pull up another example. Here's another case where it's reasonably linear on the east, but then on the west, there's another diversion through a little bit over 30 degrees. So almost certainly there are local effects that are going on here. But it's perhaps also worth pointing out that if you see, so these are asymmetric jet changes. On the west, it's going linear in a direction comparable to that on the east, then it diverts sideways. But when you see jets move in a very similar way to one another, and I don't know if you can make out here, Cygnus A's jet is very linear and then it curves. Katherine Steenbrugger and I think in 2008, actually applied a precession model to Cygnus A, and we found that you could explain, let me use a pen as a visual aid, you could actually explain some of the subtle changes in Cygnus A's jet shapes if you say that the jet axis is precessing, that is tracing out a cone, where the cone semi-angle is about 1.4 degrees. Now, I think it's probably true to say that precession would only be the explanation for why jet angles change if it's symmetric, if you see it on both, for both jets. So lots of different explanations, I think.
Yeah, Sanyukta Agarwal has another question in the chat. which is again interesting. Do all supermassive black holes produce such jets, or is there something particular about the ones that do?
That's an important question. So we think something like, well, it's certainly less than 10%, maybe it's only 5% of supermassive black holes at the centers of massive elliptical galaxies give us these jet systems. But it's important to ask, is it the case that only 5 or 10% of supermassive black holes give us these radio jets? Or is it the case that the life cycle of any jet episodes is only about 0.1? And so therefore, at any epoch, when we might observe now and in a billion years' time, only 5 or 10% of the supermassive black hole population are actually going through a jet episode. Either of these explanations warrant serious investigation, I think. We did actually do, I mean, just sort of following on from that, Carlo Nipotti and James Binney and I did a study comparing the fraction of quasars that are radio loud compared to the fraction of quasars that are radio quiet to radio loud, or radio loud to radio quiet. And we compared that with the duty cycle of radioactivity, jet activity in microquasars, in X-ray binaries. And we found that that was about 5%. So that paper is Nipotti, Blundell and Binney in 2005, if you're interested in pursuing that a little bit.
Thanks, Katherine. I think most of the questions in the chat you've answered in some form. You've taken account of which have been asked. So I'll just leave it to the floor if anybody wants to unmute and ask a question. Is it okay, Katherine, for just another?
Of course, of course.
So please feel free to unmute yourself and ask your question if you have any other questions.
Excuse me, ma'am.
Hello.
Yeah, I'm. So I had asked about why the lobes were facing only two opposite directions from the black hole. So you had said that the jets are emitted from the nuclear matter. So is the nuclear matter the same as the accretion disk of the black hole?
I would say that the nuclear region is really a very general term which encompasses the black hole, the accretion disk, the launch, the jet base, and any other material that's swirling in towards the accretion disk, and together with any wind off the accretion disk. So broadly speaking, then you might consider the nuclear region is perpendicular to the jets, but nuclear region or core is a very generic term where we just sort of lump in all those things together and the jets come out of it. Does that answer your question?
Yeah, so my actual question was, so black holes rotate, right? So will the nuclear region also rotate along with the black holes? Yeah, so if the nuclear region rotates, won't it span the entire plane? So won't the jets be emitted in the entire plane and the X-ray loops, will symmetrically cover the black hole? So why is it only in the two directions?
So you're absolutely right. We think most black holes are spinning, and some of them indeed are spinning quite fast. We also think that matter, say at the center of a galaxy is, let me do it this way, is swirling in. Whatever matter is swirling in, attracted towards that nuclear region by the potential well of the black hole, as it swirls in, it will gain in rotational speed as the radius of its orbit decreases by the conservation of angular momentum. That material is swirling in faster and faster and faster as it gets to the center. But by this point, it's very, very localized. And probably, we don't really know for certain, but simulations show that it's along the poles of the rotation that the matter is then squirted out. It's the matter that's squirted out as jets is very, very finely collimated, very, very finely focused in, relatively speaking, these narrow beams, these collimated jets. Now, we're beginning to wonder, in the case of nearby microquasars in our galaxy, as to whether what actually gets launched from the accretion disk is actually a little bit ring-like. So it might be what these jets are really composed of is rings from the innermost orbit of the accretion disk that fragment and then break out into the jets. It's probably only the innermost regions of the accretion disk where the material is orbiting very, very fast, that are moving fast enough to be able to escape down the poles. So they've got to be fast enough and close enough, we think. But that's why it's not the entirety of the accretion disk that launches a great big huge jet, we think. But there's so much about jet launch we don't understand. So I do encourage you to keep asking these questions.
Yeah, thank you.
Thank you.
Hello, ma'am. My question is that you told that it might be the case that only handful of supermassive black holes might be emitting this kind of jets. So, and another possibility may be that the jets are not much long living so that we can detect it. So my question is that, like, what might be the cause of other supermassive black holes not emitting the jets? Like, is it because that there is not sufficient matter to feed into the black hole to power the accretion process?
That could well be an explanation in many cases. If you don't have enough gas, if you don't have enough matter, it might be that, you know, any jet that you launch will be very, very weak indeed. It's also possible that it's something to do with the magnetic field configuration. If the environment is too dense, say you're in the dense environment of a spiral galaxy, maybe you can't actually create the kind of magnetic field configuration that enables the collimation of those jets. Again, as with the previous question, we definitely don't know all the answers to all of these questions. So for you and for our previous questioner, I would say, keep asking these questions, get stuck into the literature, assess what you read in the literature, decide whether you think it's a complete or a good explanation, and try and test it and see if you can refute us. And then we as a community will learn something new.
Thank you.
Thank you very much indeed. Well, goodbye everybody and keep well.